this talk is going to really focus on functional reactive programming, what that means, and to really understand how functional reactive programming is helpful for GUIs from games to more traditional kinds of web apps. And so the real key underlying question that sort of necessitates functional reactive programming is, how do we do graphics in a purely functional way? So we know the OO way of doing things, where you go and you have a thing and you modify it. But is there another way? So that's really how this got started. So to understand functional reactive programming, you really need to take a step back and start with functional graphics. How do we, from building blocks, get something that's purely functional and composable and has all these nice properties that we're used to as functional programmers, or that we find foreign and weird if we're not functional programmers. So the key goal here, this is really how Elm got started, is I wanted to make graphics simple and declarative. I had been doing some work with HTML and CSS, and I was a little frustrated where things were a little weird, and so I started wondering, how can this be done in a nicer way? And for me, functional graphics sort of broke up into three distinct parts. There's text and links. This is what we're used to on the internet. There's layout, and there's also freeform graphics. And so when you have something like text and links, it's really about text layout. How do we put these words next to each other? How do we make them flow in a container nicely? But when we start asking layout questions in this same world, we start to get weird questions. So you say, okay, I want to vertically center something here. So I have some text, and now I want it right in the middle of the page. But we're starting to stretch our abstraction, right? When you use LaTeX or you Microsoft Word, there's a reason there's not a vertical center option, because when you're working with text, it's really a weird fit. And so there's also this world of layout, where you want to stack things and layer things. And when you ask, how would I design something for layout and how would I design something for text, I would contend that you end up with different abstractions. And finally, there are freeform graphics. So these are crazy shapes that can go all over the place, getting scaled and rotated. And again, it's in a separate category of layout. So with layout, you want to be able to say, I'd like to stack these on top of each other, please. And then when you have a triangle and a circle and you say that again, you're like, well, what would that really mean? And that's an interesting question, but it's not necessarily one that's useful, in that if we try to combine all these things, we're going to get these weird parts where the abstraction doesn't really fit any of the particulars that we want to do. So Elm introduces distinct abstractions for each of these. So it has text, elements, and forms. So when we look at this in practice, oops. All right, how can people see this all right? Should this be bigger? In the back, it's all right? Okay, so we're going to start with a really simple one, as text 42. And you can see we got a little number 42. So if we wrote down the type of main, we'd say main is an element. And what this means is main is a rectangle that you can stack and lay out nicely. And this little as text function is taking basically anything we care about, or any sort of value, and showing it on screen. But there are lots of other kinds of elements we can show. So say we want to do some basic, we want some words. Okay, so we created, this is called a Markdown block. You can just put arbitrary Markdown in there with links and all the standard stuff. And when we set our main to words, this is what we see on screen. And so again, this is another element. So when we add a type annotation, we can say element, and we're nice. So we have a way to talk about text. We have a way to, let's have an image. So I want an image that's 200 by 200 of Yogi Bear. And when I try to show this on screen, again, it just shows up. So we have these basic building blocks of things that you want to have in containers. So sometimes you want words in containers, sometimes you want images, sometimes you want video, so on and so forth. And so once we have these basic elements, we want to be able to start putting them together. So Elm introduces this flow function. So flow, types aren't showing up. Normally, type annotations show up here. So this flow function is going to take a direction and a list of elements. So we can say words and then image. And then I can see these things stack up. And so, okay, yeah, we know how to stack things. But if I say flow to the right, we have this as well. Yogi is chilling over there. And we can flow inward, outward, so on and so forth. So you get these ways of combining elements that's very natural. And so you can start to create much more complicated layouts in a very simple way. You say, okay, I know I want a row of these things and a column of these things, instead of trying to force that on something that is mainly, was designed for text. Okay, so let's call this a stack of things. So this is all well and good, but sometimes rectangles don't cut it. You need something more fun. You need a pentagon. You need a circle. So for this, we have a special kind of element called a collage. Let's make this one 200 by 200. And in this case, we're not taking more elements. We're taking things called forms. So I can say filled, blue, and gone with 5 sides and radius 50. So the same kind of declarative style that we used for rectangles we can use for these freeform graphics. And so here we can have a whole list of these things. So I can also say, I don't just want a filled blue n-gon, I want a outlined solid red square? No, we're done with squares. We want an outlined circle with radius 70. Okay, and so already we have a fairly complicated scene, and dotted. We can sort of mess with it as we please, dashed. And the way we did it was this very declarative interface. And so this is great for creating, sort of very simply creating these complex graphics. And one thing that's nice here is we can actually start to transform these things a bit. So we can say, I don't just want a filled blue n-gon, I want it to be scale by 2. Maybe that will be too big. Yes, you can just see the borders of it. Scale by 1.5. So when we're in this freeform space, we can start to do sort of freeform transformations. And what's really nice here is that we have this abstraction of elements, which are rectangles. And rectangles are a subset of freeform stuff. So we can say to form. So this is, you can't see the type. This is transforming, let's take words. And it's a little big, so let's scale this one as well, 0.5. And it needs to be at a rakish angle, so rotate by 30. Okay, so we went from basic rectangles to this freeform place where we can still use all the same abstractions from before. So if we don't want to just take our words, we want to take the stack of things. Again, we can just drop this in place. So this is nice and declarative and functional. So what you can start to do is abstract out commonly repeated things. So you can have a helper function that says, okay, I'm going to make this red and I'm going to make it dotted. And maybe you use that a bunch of times. So instead of having just a declarative language that has no flexibility, you have a way to say things declarative and abstract out pieces. So this is really where Elm got started, but it doesn't move, right? So we came here for functional reactive programming, and so far we've seen functional static programming. To make a proper GUI, you know, they come to your site and they're like, oh, this is really pretty, and then nothing happens. So I got to this point in this project and I was like, this is great, okay, what's next? And so one day I asked, what if values changed over time? So I didn't want to do the mutable things where you just go and change it, but what if those values actually were changing? And this kind of blew my mind. I was like, what if values changed over time? And I was like calling up my mom, like, oh my gosh, check this out, this is gonna be amazing. And like the last time she programmed was with like punch cards, and she was like, I don't know, it sounds all right. You should probably see if there's any related work. I was like, no, this is amazing. And she was like, yeah, it sounds cool. Like, I wonder if anyone else has written about this. So for a couple days, I was like, and then I found out that in 1997, there's a really wonderful paper called Functional Reactive Animation. And this was really the first paper on functional reactive programming. So I was late by like, 14 years, but it's still very exciting. And so the ideas laid out here are actually very common in a lot of the more imperative iterations of functional reactive programming that exist today. And so what Elm did is, since 1997, there's been a lot of research continuing in this tradition of functional reactive programming and solving a lot of performance issues, a lot of abstraction issues. How do we make this really nice? And so Elm is coming after 15 years more of research and trying to get really nice answers to how can we make this efficient, how can we make it pleasant to use. So finally, that brings us to the beginning, functional reactive programming in Elm. So what does this actually look like? And the key concept is called a signal. And this is a value that changes over time. And various different frameworks and projects will call this a different thing. But you can think of a signal as a value that's changing and sort of it updates in discrete increments. So one example of this is mouse dot position. So this is a value in Elm. And its type is not a pair of integers, but a signal of pair of integers, which is to say it's a pair of integers that's going to change over time. To make that a bit more concrete, we're going to go back here, shapes, and let's have a main equals as text. And before that gives me a type, an error. Okay, so the program we're looking at now is lift as text on a mouse position. So we remember as text from before, we just show values on screen. But in this case, we're showing the mouse position. So as I move my mouse around, it updates automatically. So you can think of lift as saying take some function and always apply it to the current value of this signal. This actually becomes quite flexible. So once we have this concept of a signal, a thing that changes over time, we need to be able to transform signals. So this is the lift function you saw. So we're taking a function from A to B, we're taking a signal of A's, and we're getting out a signal of B's. So we're doing a transformation on the latest value. So the example we saw is, it's pretty straightforward, but we can do something a bit more exciting. So let's say we parameterize our collage by X and Y. And instead of scaling by 1.5, we scale by Y over 100 cast properly. This is why you have to practice the live coding sections so you don't get type errors. And let's rotate this guy by degrees to float X. And okay, and shapes. So quickly we'll go through, I should just demo this. So as I move across the screen, we see the pentagon rotate, and as I move up and down, we see the circle scales. And what's cool is this code essentially didn't change. We still have the same declarative structure, but we parameterized by X and Y. And so when we say, I want it to be at degrees X, well, whatever X is, that's what we'll do. And so when we lift the mouse position, this pipes through. And so what's nice is as you add interactivity to your application, you're not fundamentally changing how you wrote everything, right? You don't have to write it the static way and then rewrite it to be interactive or like hook into it and do all sorts of crazy manipulations. And so this becomes very flexible. So we can switch out mouse position with, well, with lots of other things that we'll see in a moment. So right now we have interactivity, but we have interactivity right now, right? So again, someone comes to this website and they're like, oh, sweet, it's moving all around. And then they're like, how do I pay for this? And they start typing in, but it only remembers the current keystroke, right? So they say, oh, my name is da, 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 and then it disappears as it goes along. So we're only talking about the present. So to really make this robust, we need to be able to, we need to also be able, I'm going to come back to this. We need to be able to depend on the past. And so the key function we use for this is called fold_p. And this should remind you a bit of fold_l and fold_r, so, or reduce depending on what your background is. So you can think of fold_l stands for fold from the left, fold_r, fold from the right. This stands for fold from the past. So as updates come in on this signal, we're going to say, OK, I got this value. I have my current value of this thing. And I'm going to give a new one out. And that's what we get as our signal of B's. So as new updates come in, we can remember what happened and make our application depend on that. So when we go back over here, we can start to write a little bit of past-dependent code. So let's say lift as text onto fold_p of, we'll write a function here. OK, let's first start with keyboard.arrows. So this is a built-in function that when I press up, y is going to go up. When I press down, left, right. So we're representing the state of the arrows at the current moment. And this is using Elm's record notation. So you can access with like .x and .y to get into these things. So this is all well and good, but let's say we want to actually, when the user presses up, 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 we want to keep track of how many times they've pressed up. So we can use fold_p. We have a counter that starts at 0, and then we need to say, oh, the docs are working now. So this is Elm's version of lambda or anonymous function. If you squint hard enough, you can see it looks like a lambda. There is Unicode support, so if you have a magical keyboard, you can use it, and you also should tell me, because I want to use it. So we take in this pair of x, y, and we take in our counter. So we can say counter plus xy dot y. And we're getting a little bit long here. OK, so I just have a number now. And when I press up, it's going up. OK, this is proof of actually pressing the button. So up, 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 down, 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 down. So as events are coming in on keyboard.arrows, we're saying, OK, take our counter and take the y of that. So when you're not doing anything, it's 0. When you press up, it's 1. And so we're incrementing our counter. And we can be a little bit more fancy about this. So maybe we want to also keep track of x and y. So we maybe start at 0, 0. And instead of having a counter, we have a position. Oh, I'm getting lots of x's and y's. So I'm going to say this is our direction from the keyboard. Oh, arrows. Direction. OK, are we clear? Direction. I'm going to call it direction. I'm committing. And then we have a x and y from what is our current position. And so what we want to say is I want the current position, x position, plus the x direction. And we want the current position y plus the y direction. And again, so as I press up, 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 down, 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 left, 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 right, 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 right. So, and again, this is starting to look a bit like our mouse position. We have a tuple of integers that changes over time. So instead of saying as text here, we can say shapes. And we probably should multiply things by like a lot. OK, let's not though and see. OK. it jumped because the size of the canvas is a little big. Okay, so you have to press a lot of things, and then I don't think this one will even show up. Oh, there it is, there it is. Okay. Okay, you can see it. Okay, and the real solution was just to multiply by 10, so I could have done 10 times less work. Okay, now it's easy, you know? Okay, so the same code we wrote before that was for dealing with mouse stuff is now working with keyboard stuff. And this wasn't the right direction to go. The really cool thing is that now that we have keyboard arrows, it's pretty simple to start making a shape that moves around. So it's going to be Yogi. It's got to be Yogi. Move to XY to form Yogi. Oh, he's called image. No. Oh, okay. Yeah. See, you practice, but you know you can't get it perfect every time. To float. Okay, so we have Yogi Bear. Ah, he's too big. Fortunately, we can scale him. Okay, we have Tiny Yogi. Oh, crap. This is, yeah, bigger screens. Okay, so when I move him around, he's just moving around the world, just like hopping around, and he can sort of be like, whoa. So we haven't done a ton of work, right? We sort of messed with how we keep track of what arrows have been pressed. And we said Yogi is at X and Y position. And we have the sort of basics of a little guy who can like move around the world, which would be kind of crazy to do in another setting. And so let's see how far we can get with this. Oh my God, how did... what is going on? Why? It's got to be monospace. This is not... What? Okay, give me a second. Oh, of course. So, thank you. So this is the beginnings of a little Mario program, and I filled in some details because we've kind of covered them already. So it breaks up into 3 distinct parts. We have a model of what is it that we're trying to represent. We have a way to update that model, and we have a way to display it. So if we look at the display, I'm going to get you guys to focus on this section. So it's a collage that we've seen before, and we want a rectangle. Oh, so this notation, I might use this a bit. It's application, if you know F#. So saying f of x is the same as saying x is given to f. So it's a way to save parentheses, and I know that's a controversial topic here. But it's possible. I'm not saying it's right or wrong. So we draw the sky, we draw the grass, and we draw Mario. And we won't have to change this throughout all of the updates that we do. And one fun thing is, okay, we'll get to that later. Okay, so our model is basically saying what it means to be Mario. What is Mario at his core, in his soul? He's an X and Y position and an X and Y velocity. This is really what we need. This is what it means to be Mario. And then we have a way to update Mario. So we're going to take some inputs from the world. Maybe that's keyboard, maybe that's time. In fact, it's actually both of those things. And we're going to update Mario somehow. And so this all gets put together in a section that I've labeled Mario. I don't know exactly. I haven't gotten the right name for this section. But Elm code's always going to break up into these 3 key parts and then another part to like put things together. And you shouldn't always call it Mario. So let's, at the moment, look at what input means. Okay, so right now input is set to FPS 25. So this is a built-in thing that's going to give you a steady frame rate of 25 frames per second. And
it's a signal, right?
Yeah, it's a signal. So this is changing over time. And what we're seeing here is a time delta that's spit out at as close as it can get to 25 frames per second. And it's hovering around 40 milliseconds. And if you do the math, That's right, right? We're getting these frames, time deltas. And so when we look at how we're putting everything together here, we're saying fold P, fold from the past. We're taking our inputs, so this is a time delta, and we're stepping Mario forward by these time deltas. So when we look at the step function, which is too far away, it is taking these time deltas, or in mathy words, delta time. We can start to mess around with Mario. And right now, we're in that same place we were before, where we have a Mario game, and it looks really promising. We're like, oh, how do we get started? And it doesn't do anything. So the first thing we want to add is probably gravity. So we're going to take, oh, no, we don't want gravity. Before we have gravity, we need physics. What was I thinking? OK, so we take DT and Mario, and we can just say, all right, I want Mario where, so this is Elm's record update syntax. So records are kind of like objects, but kind of not. And so what we're going to be saying here is take Mario and update these particular fields. So you want to change Mario's x to be mario.x plus mario.vx, oh my God, dt. Okay, so we're taking his current position and updating it by the velocity and the time that has passed. And to be a little more consistent, we should do that with his y as well. Mario.vy times dt. Okay, so we have physics now. But despite that, Mario is just sitting around. So something has gone wrong. So if we look at our model, we gave very boring starting things for his velocity. So if we switch this around, we see that physics is working. So this game is, I don't know, this is one of my favorite iterations of the game. Like, I kind of am always sad to change it from this. And there's a kind of like sadness when he goes away. You're like, oh, did I win? I don't know. OK, so let's have him stand still. And now that we have physics, we can actually start to mess around with changing the velocity ourselves. So let's say we have, oh, this was the function I said we were going to come back to. OK, we came back to it. Perfect. Yes. So we have this function called lift2. And it's a way of combining two signals. OK. Keyboard.arrows. So keyboard.arrows we saw from before. And then I did a bunch of stuff that I didn't explain well enough yet. OK, so we're looking at our input, and we added a bit to it. So this operator here is saying take two things and put them together in a pair. And we have the same FPS, and now we have keyboard.arrows. So when I move around, we see those things move around. So our new input isn't just dt. It's actually a time delta and a direction. OK, so, oh, I didn't actually do it yet. So let's make Mario walk. And we're going to give him an x, which way he's walking. And so we can say Mario equals Mario where his Vx gets set to x. No? Oh, man, this is always the hard part. Actually applying the functions that you've written. OK, so Mario zooms around like a maniac. I'm impressed that he got back to the same spot. So let's divide this by like a lot. OK. OK, so this is more reasonable. We have Mario, and he can walk around. And this is good, but he can't jump. I'm trying to jump. He's trying to jump. He really wants to jump. He knows that he needs to. His life depends on it. Because when the Goomba comes. OK. So let's have a way to jump as well. Mario, where Mario. So in this case, we want to probably mess with the y velocity. And to float no, that's crazy. There are specific cases where we want to be able to jump, right? So if someone presses down, we don't really want to jump. That, like, what does that mean? Like, I don't know. So we want a specific case. If y is greater than 0, okay, if someone had pressed up, then we want Mario's velocity to change to, let's make it 0.5. Otherwise, we want Mario. We don't want to change anything about him. So we can say jump, dir.y, do all those other things. So we have our same old Mario. He can walk around. And then when we jump, he flies away. So again, this is pretty great. I like this a lot. But it's not very practical. I guess it lets you win because you can just jump and then just like fly across the whole world and finish it like way up in the sky. But this is not ideal. So now we actually do need gravity. See, gravity, it comes later. I found it surprising also that like part of Mario is like you need to write gravity. I don't know. It seemed okay. Anyway, let's do it. So we want Mario so gravity is going to act on the velocity. So we have his Mario where his y velocity gets updated to be his current velocity plus, no, minus, that'd be some freaky gravity, minus dt over a lot. No, that's too much. No, okay. And of course, we have to apply the function. All right, this is going to be great. Does anyone see what's going to happen? Okay. So we're doing pretty well. We have gravity. And it's cool because it feels like he's falling to the center of the Earth. But if you think about it, his Earth really is flat, and he's just falling. There is no center. I don't know. Okay, so I think that means our physics is wrong, right? So like we can't just have him go down. We need to have him stop at some point. And so we can do a little trick here. So we can say his new x is going to be the maximum of 0 or whatever physics determines it should be, right? So in the case of he goes negative, we say, no, no, no. We actually want him to stop at the Earth, well, the infinite plane that he lives on. Okay, so we try this again. And we have Mario walking around. We have him jump, and it's nice, but it's like it's not perfect because like when we can actually jump at any moment. So this is like the ultimate hack. This is like Elm or Mario no clip. So we can just like go across the world, and the Goombas are just like, oh, I'll get you. So we need to do better. So our jump function just says, is the person pressing up? Well, yeah, but we need other constraints. Mario can only jump when he's on the ground. So, and Mario dot y equals 0. So now his world is getting smaller and smaller. So now when I try to jump as high as I want, I can't do it. I'm just holding down, right, or holding up now. So he's like, he remembers times when he could fly. Okay, so we have a lot of stuff going on here, and the code we wrote was, I mean, this is our update section, right? So we wrote these nice little functions that we can test independently. How does gravity work? And okay, gravity's fine. We need to mess with another part of the world. So we saw gravity was always working, but physics wasn't stopping the ground. And so you can think of these very independently and then just compose them together. We put together our two inputs. And one last thing that we might want to do is we have this render function. So like right now, Mario like exists just like frozen. He's like, but we can do better than this. And what's cool is we don't have to mess with any other part of the program except display. So Mario is an argument to our render function. And instead of just we have some source images here. Instead of just saying, okay, Mario is going to stand to the right, we can give Mario a verb. So if So this is going to be using Elm's multi-way if, so you can have a bunch of branches. So if Mario dot y is greater than 0, he's jumping. And if Mario dot vx is, not equal to 0, then he's walking. Otherwise, and so otherwise, this is just an alias for true. So it's like, okay, we'll do this. And so once we get to a true thing, we're going to hop to that branch. So otherwise, Mario is standing. And due to careful GIF construction, we can just add this in. And okay, so when we jump, he's actually, woohoo. And when we walk, you can see him very brisk pace. When he walks backwards, moonwalk. Okay. I wish I had the music for that, right? Just like Michael Jackson. Okay. So we also have this information, though. We actually know which way he's facing. So we can say direction equals if Mario dot vx is less than 0, then left. Sorry. Else right. Okay. And so we can add this in again and again. Carefully constructed GIFs. So now he walks this way, and when he walks the other direction, he actually is facing the right direction. Now there's one problem left in this. Okay, so he jumps, it looks fine. He walks over here. Now, when he walks to the left, he flips around. Because we say, well, if it's less than 0, then left. But we actually mean if he was walking left, then we want to keep him facing that direction. And what's interesting is when we look at our model, we actually don't have that information. There's no way to know where he was facing last. And so that means when we want to add something like this in, it's very clear we need to go to our model. We need to actually put this into our well-defined system of what it means to be Mario. It turns out I was being overly simplistic. He also has a what direction was he going. And that means we have to change our update a little bit, and that means we have to change our display a little bit. But each of them is an independent piece. And when you need to modify something, it always points back to, is your model correct? Do you have the right way of thinking about this? And so I am not going to go through what it means to mess with Mario in this way. Perhaps this is an exercise, but that's a fun one. I almost fit it all on one screen. So this is the whole program, and we can look at line numbers. So we have 42 lines. Okay, we have that doesn't count. We have, so let's call it 40. Let's call it 40. We have 40 lines to make sort of Mario walk around and sort of do all these things. And each step was fairly straightforward. And so I think this kind of approach scales well to general GUI problems. So this is very specific to how Mario works, but the scope of problems that exist for GUIs is much larger. We've asked what if values changed over time? We've sort of gotten a taste of that. And I sort of wanted to take an opportunity to say, how has Elm changed over time, and where is Elm going? So I spoke at Emerging Languages Conference last year. I felt this would be a good time to reflect on what have I been doing with my life since then, and sort of what's happened to Elm. So there's a timeline of what we've seen today. So the sort of key things that have been going on have been, it started with concurrent FRP. So this is sort of the theoretical foundation of how Elm works. Ideally, we can get concurrency working, but with JavaScript, it's a bit harder than it would be on other platforms. You have these trade-offs. There's also Markdown support and extensible records. This is something that I'm really excited about, but I don't get to talk about a lot. But it's a very flexible way to have records in a statically typed way. So we saw we can update things, but in fact, you can extend things and delete things from them and put them together in a way that is very uncommon in statically typed language. So you get a lot of the flexibility of something like JavaScript, but in a way where your compiler can say, hey, you're using X, but there is no X. There's no more like accessing .x of undefined. And this all led to a PLDI publication. So this is a programming language conference. And sort of this was all about how does concurrent FRP work and how does this fit into the research that's happened since functional reactive animation in 1997. And so after sort of this time period, I joined Prezi. So I'm now working full-time at Prezi. This is a Prezi. I'm working, normally I write it in Elm, but this time it's a Prezi. I started working at Prezi full-time on Elm, so sort of focusing on what happens next with Elm. And so that has meant the scope of the project has been able to get a lot bigger. So I'm thinking about like, what's the path to practical FRP? How can we use this in industry? What problems are a really good fit for this kind of thing? And so you can think of what I'd been working on before as kind of the theory side of things. What are the underpinnings of this? How do we get them efficient? And now I'm moving more towards practice. Like, how do we make this accessible, approachable, and useful in a production environment where there's other code living? So the key things that I've been focusing on since then is how to integrate with HTML and JavaScript, how to debug. This is a common question that people ask. And so, and also, how does FRP look for traditional GUIs? So you have your text boxes and buttons all interacting and form validation and so on and so forth. And so the key features that have been happening since then are actually doing HTML embedding. How do I put an Elm program into a tiny box on screen? So when you pitch to your boss, you say, okay, I just need this 100 by 100 square. Like, I don't need the whole page. Fixing up the type checker. So it turns out type checkers are hard. I don't know if any of you guys knew that. It's like a little tricky. So one of the big projects that happened since I joined Prezi was actually getting a really solid, efficient type checker. And so when you mess up, Elm's going to say, hey, like, I see what you did there. Here's what's going on. Another one is hot swapping. I forgot to show hot swapping. Hot swapping, okay, there's time for this. So we have our Mario program, right? And we have this hot swap button, which I like mysteriously never pressed. And so let's look, we have gravity. And right now it's at 400. Let's make it 100. Now, keep in mind that the state of Mario is based on what we've done throughout the program. And so we changed this gravity function. And when we press hot swap, the state is maintained. But now when we jump, I moved it in the wrong direction, didn't I? Yeah, I want weaker gravity. That's no fun. Okay. Yeah. Hot swap. Okay. Okay. And so what's nice is you can go arbitrarily deep into your application. So maybe you have a bug that only happens 10 minutes in. You can go to that particular place, tweak your code a little bit, hot swap in, and see if that fixes it. And you're like, no, okay. And so there's a guy working on a debugger that will let you rewind so that you can actually retry these things again and again. Okay, and so that's hot swapping. And this is, in a lot of ways, thank you. This is like a debugging tool, but also like how can we program in a more expressive way. And finally doing some industry talk, sort of saying this is what FRP is about. How does this fit in with what you guys are focusing on? How can this fit into, like, how can we do a widget in Twitter that does this or something like that? And so what's next is there are 2 projects on the way. These are some of the short-term ones. One's to do FRP. The idea was that to do MVC was kind of like the basic proof of concept of any MVC library. And so the goal is to do a basic one of these in Elm. So it's a little rough graphically. This is in the works still. But we can say, OK, go to the store. This is a very basic to-do list. Like, we need every step of the way. Get milk, drink milk, pay for milk. And we can just get rid of these things as we please. And so again, this is a little demo Elm program. And the internet's not working, and I don't imagine that this is incredibly readable. But the point I wanted to make here is that it breaks up into these same parts again. We have a model, we have a way to update it, and we have a way to display it. And so when we look at our display, oh my God, this isn't, OK. 5 minutes? Oh, it's past. Okay, so that's a practice path. That's functional reactive programming in Elm. Thank you very much.